Hello, and welcome to this lesson in quantitative reasoning. We are in the logic unit, and this is part one of two videos on the evaluation of logical statements. Now, this section, we're only going to cover the evaluation of negation, conjunction, which is and, or disjunction, which is or. In future videos, future sections, we will also include the conditional and the biconditional statements, the if-then and the if and only if. So, this was made by your textbook, so I'm going to show that. And here is really what we're going to try to do is just evaluate. It means find a value for a logical statement. Now, when we say logical statement, we mean a compound statement that's composed of simple statements joined together with connectives. So we're going to look at constructing, they call this a truth table, the way they do this, construct a truth table with only conjunctions and determine the truth value, with only disjunctions. And then in the second part of the video, we'll get into using both, and we'll get into using three statements together. The first part of the video, we'll see only two statements put together. So determine the truth value of a conjunction. When you see the word conjunction, and most of the time you'll see conjunction, you should be thinking the symbol is A and it means and. So it is a connective. P and Q is how you would read this. To determine the truth value, the only time a conjunction is true is if the statements on both sides are true. If either side is false, you immediately write false over here. So that's how you evaluate a conjunction. You look for the places where they're both true. And if that is the case, then you write true. If either statement is false, it's immediately false. So when you say and, you are saying both of these things I'm saying are true. So if either one of these is false, the whole and conjunction compound statement taken together is false. So here is what we call a truth table for P and Q. There are two statements. So what the truth table for P and Q is it wants to include all the possible combinations of P. Now, P can be true or P can be false. Q could either be true or false. So if P is true, Q could still be either true or false. And then if I draw I'm drawing a possibility tree here. Q could still be true or false. So what your input rows, this is called a row, this is called a column, what your input rows have to include is all four of these paths. You can see I have a path that goes true, true. P is true, Q is true. That's the first row. I have a path that goes true, false. That's the second row. Then if P is false, Q could be true, so false, true, then false, false. What's really important here is that every time you have a two-statement truth table, what you do is you go left to right in alphabetical order. P comes before Q. So if you had A and B, you would do A, then B. If you had ST for your variables, or even STU, you would go in alphabetical order, labeling the tops of your columns. For two statements, you have four rows. And you always put the true falses in this order. You start the leftmost with two trues, two falses, and then it alternates true, false, true, false. That is how you get these four paths. Now, certainly if I wrote the falses first for the P, I could have still had all four paths represented. But it's important we have a standard way to set up our two-statement truth tables. There's going to be four rows, and we're going to start with the alphabetical order leftmost statement. Half of those rows will be true and half will be false. And then for each of the rows that were true, half of the Q's are true, half of the Q's are false, so you alternate true, false, true, false. Every single time you set up a two-statement truth table, this will be what the first two columns look like. If you do it in a different order, I'm going to mark it wrong. And the reason for that is later we start to compare two different statements to see if they are equivalent. If we don't set up our inputs the same, we don't know, we have to compare them a row at a time instead of just looking at the whole column. So you're going to set up every two-statement truth table in this pattern. True, true, false, false. On the leftmost, then true, false, true, false. Now, where do we get these values? Well, this table, I'm going to erase what I just did. Okay? You can always rewind, but I'm going to erase all of this stuff. Because this table here, I want you to see that as a whole thing. These are our arithmetic facts for the and. You know how when we learned to add, we did 3 plus 2 is 5, and you had multiplication tables. Certainly you did multiplication. You had a table that you may have memorized. It showed you 5 times 5 is 25, 5 times 6 is 30. This is kind of what that is. P represents whatever's on the left side of my and, and Q is whatever on the right. So when the left is true and the right is true, so when both statements are true, the output is true. And it turns out the order doesn't matter for the conjunction. Whenever you have both the left side and the right side are true, the result of the whole thing taken together is true. So a true and a true is always a true. Anytime any of the statements involved, there's 2 statements involved, there'll never be more than 2 statements at a time you're looking at. So I have one side is true and one side is false, I get a false. And it doesn't matter which side is true or false. As soon as you see a single false involved in one of the statements in and, you know the result is false. So the only time an and is true is when they're both true. And this table shows that. The result of a true and a true is a true. The result of a true and a false is a false. The result of a false and a true is a false. And the result of a false and a false is a false. So that would be very important to know. All right, so knowing that, let's do some practice. So I have four statements. I'm not going to make the truth table for these, but I'm going to try to determine whether the statements under here, which are made with conjunctions, are true. So here we go. So statement A is 1 times 2 equals 3. Statement B is 1 plus 2 equals 2. Notice these are all statements. They're math statements, so they can be given a value of true or false. Statement C is 3 times 2 is 6. Statement D is 5 plus 2 is 7. So it might be helpful to write down the truth value for these statements. 1 times 2 is not 3, so statement A is false. 1 plus 2 is not 2, so statement B is false. 3 times 2 is 6, so C is true. 5 plus 2 is 7, so D is true. Part A asks me to do A and B. Well, the value of A is false. The value of B is false. A false, and I only needed one false, gives me a false. If I look back at my truth table, when I have a false and a false, I get a false. So B and C. Well, statement B is false. Statement C is true. I have a false and a true, but it doesn't matter. In order for the and to be true, they must both be true, so that's a false. Statement C and D. Statement C is true. Statement D is true. Oh, 2 trues, that's how I get a true using an and. And the last one is A and D. A is false. I don't even need to write down what D is. I already know my and is going to give me a false, but I'll complete this. So out of all of these, the only one that was true was the one that used C and D, because you need 2 true statements when you join with the connective and to create a true compound statement. So hopefully you're seeing the bit of the reasoning there. Now, what if I use a different connective? Well, or is a little more forgiving than and. Or only requires one of the things at least to happen. So the only time an or is false is both statements false. So it's easy to figure out when an and is true, because that's only when both statements are true, and it's easy to figure out when an or is false. Any other time, as soon as you see a single true and you're using the or connective, you're going to say, oh, this is true. So if at least one is true, a true or a true is also true. Okay, so they can both be true. So they have that has that in common with the and. So the only way it can be false is if you have 2 falses. It's kind of sort of the opposite, but not really of the and. So let's do some practice here. Statement P, 4 times 2 equals 9. Well, that's false. 1 divided by 1 is statement Q, and that's true. So P or Q, that'll be a false or a true. So that'll be true. The truth statement for OR, I wish they had shown you that. I'm going to draw the truth statement for OR here, the truth table for OR. So I'm going to use, for truth tables for connectives, there's only ever 2 variables, so there's 4 rows. So I set up, I'm just going to call my variables P and Q. That's pretty standard in logic. They could be other letters, but when textbooks write about logic, they usually start with P and Q. So look, true, true, false, false. There's my 4 rows. Now, in row 1, what is the value of P or Q? Well, for OR to be true, I only need one to be true. Well, in row 1, I've got 2 trues. So that's a true. In row 2, true or false. So in this column here for OR, in each row, I look to see what's the value of P and Q are in that row. So I have a true or false. All I need is 1 true to be true for the OR. In the 3rd row, Q is true, so I'm all set. But in the 4th row, both are false, so the output of P or Q is false. This kind of reasoning is used in digital logic design, where you have a switch. An OR would be a parallel circuit with 2 switches, and as long as one of them is closed, your light bulb will light. An AND would be 2 switches in series, and you need them both to be closed. We're not going to get into that in this course, but certainly friends in engineering, they're going to do that in their digital logic course. You actually create digital circuits. The computer you're using is based upon these principles. So here is your truth table for OR. You should know this. What you should really know is that for an OR, if all you need is one side to be true and the whole thing is true. If they're both false, is the only time you get a false. So let's move on. I think we're about done because we're going to go into 3 statements next. So the 2 things we've learned in this video, this is the truth table for OR. And the other thing we saw was when you had an AND. So let's look at this P and Q. We can use the same, we would set up the input columns exactly the same, so I don't have to write them again. In the first row, AND will be true because both are true, but in all the remaining rows, there is a false, so the AND is false. So these are your math facts for the connective OR and the connective AND. You should be able to keep those symbols straight now. You should know the difference in your head. Remember the AND you can tell because you can draw a line through it and it looks like an A. So if you draw a line through this, it doesn't look like an OR. But if you draw this one through, it does look like an A. So that's the AND. The other one must be OR. All right, join me for part 2 of this video, and I'll see you in class.